Bismillahirrahmanirrahim. Assalamu alaikum. Hello students, welcome to the electrical engineering channel. In this lecture, I am going to discuss the differential volume element to calculate the divergence of electric flux density. So, in this demonstration, I will evaluate this closed surface integral of Gauss's law, and then I will equate it to the net charge enclosed, and this derivation starts from this integration. So we have a rectangular closed surface or a cubical closed surface, and this is our point of interest, which is lying at the center. And the electric flux density at this point is equal to dx naught ax plus dy naught ay plus dz naught az, and the coordinates of this point are p, x, y, z. The differential volume of this element is equal to delta x, delta y, delta z, right? So these six surfaces will constitute the entire closed surface. So this integration will have to be evaluated for these six surfaces. So first surface is the front surface. This is the back surface. Next surface is the left surface. This one. Next surface is the right surface. And then we have a top surface, and then we have a bottom surface. So the first integration is the integral over the front surface, and this integral is equal to d dot ds at the front surface, and it is equal to d front dot delta s front. So d front is actually dx front into delta y into delta z. So this is the front surface, and the incremental area of this surface is delta y into delta z, and unit vector is ax, right? Because the unit vector is the normal component or the normal drawn at the surface. So for this surface, the normal will be in the direction of x-axis. So delta s will be equal to delta y delta z into ax. So since we have ax over here and we have a dot product, so x component of the electric flux density will be considered over here. So dx front into delta y delta z, and dx front, the density for at this surface will be equal to dx naught, the x component of the density at the center, plus delta x by 2. Delta x by 2 is the distance of this point from this front surface into rate of change of ds with x, right? So it will become dx naught plus delta x by 2 into partial dx over partial x. So this is actually the Taylor series expansion of this electric flux density, and in the Taylor series we only have considered first two terms. So there are higher order terms in which we have delta x by 2 square 1 by 2 factorial into partial square dx over partial x square. The next term will be delta x by 2 cube into 1 over 3 factorial into partial cube dx over partial x cube, and so on. But for simplicity, we just have considered the first two terms because these first two terms are the most dominant terms, and as we move towards the higher order terms, their magnitude becomes smaller and smaller. So it is safe to discard those higher order terms. So this integration will be equal to dx naught plus delta x by 2 partial dx over partial x into delta y delta z, right? So this is the front integration. Similarly, we can also evaluate this back integration, and in the back integration, this will be dx back, and that will be delta y delta z into minus ax, right? Because for this back surface, the outward drawn normal will be in the minus ax direction. So after the multiplication, it will become minus dx back delta y delta z ax. Now dx back is equal to dx naught minus delta x by 2 into partial dx over partial x. Right here, delta x was positive because we are moving along the positive z direction from the center to the front face. So when we are moving from the center to the back face, we are moving actually in the negative x direction. So delta x will be negative in this case. So this is dx back, and put this dx back in this expression. So the back integration will be equal to minus dx naught, and minus minus will be plus. So plus delta x by 2 into partial dx over partial x. Now we can add these two integrations, front plus back, and it is equal to dx naught will be cancelled out with minus dx naught. Okay, so here we have dx naught, here we have minus dx naught, so they will be cancelled out. And in this expression, they will be added, and we will have delta x over here. Delta x by 2 plus delta x by 2 will be delta x. So this will be partial dx over partial x delta y delta z. So this is the sum of first two integrations. Similarly, for the left and right integrations, we will have partial dy over partial y into delta x delta y delta z. And for the top and bottom integrations, we will have partial dz over partial z delta x delta y delta z. And this delta x delta y delta z is equal to delta v. So this is the incremental volume. And according to Gauss's law, these all integrations are actually equal to the charge enclosed in volume delta v. So this is equal to these three partial derivatives, and delta x delta y delta z can be taken as common, and it will become delta v, right? So now I am going to introduce a vector operator which is called del. So this del is called vector operator, and it can be defined as partial over partial x ax plus partial over partial y ay plus partial over partial z az. So this is a vector quantity, and it actually gives us the partial derivatives of any vector field with respect to all the x's, right? So similarly, d can be written as dxax plus dyay plus dzaz. So now if I take the dot product of this vector operator and this electric flux density, I will get partial over partial x dx plus partial over partial y dy, because ay dot ay are equal to 1, ax dot ax is also equal to 1, and at the end I will get partial over partial z dz. So this thing, partial dx over partial x plus these three partial derivatives, can be replaced with del dot d, right? So this del dot d is called divergence of d. Okay, so this del dot d is called divergence of d, and from equation 3 we can write delta q. This is delta q equal to del dot d into delta v. So delta q is equal to del dot d into delta v, and from here we can say that del dot d is equal to delta q over delta v. And we also know that delta q over delta v is charge per unit volume, and it is equal to volume charge density rho v. So it means del dot d is equal to rho v. So del dot d is equal to rho v, or we can say that the divergence of d is equal to volume charge density. So whenever we are taking the dot product of this vector operator with any vector quantity, it is called divergence. And if we are taking the cross product of this vector operator with any vector quantity, it is called curl. So we will also discuss curl in more detail in the coming lectures when we move towards electrodynamics section of this course. But in electrostatics, we will just deal with the dot product of this vector operator with the electric flux density, and it is called divergence of D. So divergence of D is actually equal to volume charge density, and it is a non-zero quantity. So whenever divergence of any vector quantity is a non-zero quantity, it means the orientation of this vector quantity is actually diverging in nature, right? So whenever we have an whenever we have a vector field which is diverging from the source, then the divergence of that vector quantity will be non-zero. Okay, so electric field lines and electric flux lines always diverge from the source, so the divergence of these two vector quantities will be non-zero. So that is what we have obtained by this derivation, and this is also called Maxwell's first equation in point form. So Maxwell's first equation in point form is del dot D, or divergence of D, is equal to volume charge density. And the Maxwell's first equation in integral form is written over here, and it is the mathematical form of Gauss's law. So d dot ds closed surface integral is equal to the charge enclosed, and this is called Maxwell's first equation in integral form, and this is called Maxwell's first equation in point form. So the divergence of D for cylindrical coordinate system is also written over here, and divergence of D for spherical coordinate system is also written over here. So the derivation is actually carried out in Cartesian components, but in cylindrical and spherical components, the derivation is actually avoided, but the final expression for the divergence of D in both cylindrical and spherical components is displayed over here. So that is all about our today's lecture. Hopefully you have enjoyed and understood the concept which is discussed in this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.